across the observable universe, spanning some 93 billion light-years from edge to hypothetical edge, approximately 85% of all matter exists in a form that has never scattered a photon, never radiated heat, never revealed itself through any electromagnetic signature humanity has devised to measure, and yet this invisible scaffolding, this dark matter, determines the architecture of every galaxy, the motion of every star, the gravitational songs that govern cosmic evolution across 13.8 billion years of expansion and structure formation. Within the Coma cluster, a gravitationally bound assemblage of more than 1,000 galaxies, located some 320 million light-years distant in the direction of the constellation Coma Berenices. Swiss astronomer Fritz Zwicky first calculated in 1933 that the visible mass of luminous stars and glowing gas could account for barely 1% of the gravitational binding force required to prevent these galaxies from flying apart at their observed velocities, suggesting the presence of what he termed dunkel Materie, dark matter, an invisible component outweighing the visible by factors exceeding 100 to 1. The question implicit in this discovery, refined through decades of gravitational lensing observations, galaxy rotation curves, cosmic microwave background measurements, and computer simulations of structure formation, concerns not merely the identity of this dominant constituent of cosmic mass, but rather what transformation in human capability, what revolution in technological and theoretical understanding might emerge from learning to detect, manipulate, and ultimately control the distribution and behavior of this pervasive substrate that shapes reality at scales from galactic halos to the cosmic web itself. The detection apparatus required to sense dark matter directly, to register individual particle interactions rather than infer its presence through gravitational effects on visible matter, would represent a technological achievement of extraordinary subtlety and isolation from terrestrial noise, requiring detectors cooled to temperatures within millikelvins of absolute zero, shielded beneath kilometers of rock to eliminate cosmic ray backgrounds, and constructed from materials purified to eliminate radioactive isotopes at concentrations measured in parts per trillion, all designed to register the hypothetical collision between a dark matter particle and an atomic nucleus with sufficient precision to distinguish genuine signal from the constant susurration of background radiation that permeates even the most carefully isolated experimental chambers. Such detectors, whether employing tanks of liquid xenon monitored by arrays of photomultiplier tubes sensitive to the faint scintillation light produced by nuclear recoils, or crystals of germanium or silicon maintained at cryogenic temperatures to measure minute temperature, increases from particle collisions or bubbles forming in superheated liquids when traversed by recoiling nuclei, operate at the threshold of measurability, seeking interactions so rare that kilograms of target material might register only handfuls of candidate events per year, each requiring exhaustive analysis to separate potential dark matter signals from neutron backgrounds, detector artifacts, and the irreducible noise of natural radioactivity. The transition from passive detection to active manipulation, from simply registering the presence of dark matter particles passing through terrestrial detectors to actually influencing their trajectories, concentrations, or quantum states, would require theoretical breakthroughs in understanding the fundamental nature of dark matter, particles themselves, determining whether they constitute weakly interacting massive particles, or axions, or sterile neutrinos, or some other exotic species not yet imagined by particle physicists, and furthermore developing interaction mechanisms beyond gravity that could couple to these particles with sufficient strength to enable controlled manipulation, while remaining consistent with the stringent constraints established by decades of null results in direct detection experiments and particle collider searches. The theoretical framework enabling dark matter control would necessarily involve extensions to the standard model of particle physics, introducing new force carriers, new symmetries, or new dimensions of space through which dark matter particles might interact with specialized fields generated by technological apparatus, perhaps exploiting the same theoretical mechanisms that keep dark matter particles from annihilating with ordinary matter, despite their presumed abundance in the solar neighborhood, where estimates suggest dark matter densities of approximately 0.3 proton masses per cubic centimeter, translating to roughly 10,000 dark matter particles per liter of space, each moving through the Earth at velocities of hundreds of kilometers per second as the planet orbits the galactic center, and the entire Milky Way moves through the local cosmic web structure. The engineering required to generate fields capable of deflecting, focusing, or confining dark matter particles would likely involve energy densities and field strengths far exceeding anything achievable with current electromagnetic or nuclear technologies, perhaps requiring the controlled manipulation of space-time curvature itself through localized gravitational anomalies, or the generation of exotic field configurations predicted by supersymmetric theories or string theory models that extend our universe into additional spatial dimensions compactified at scales beyond current experimental reach, or the creation of topological defects in the quantum vacuum that could serve as boundaries or channels for dark matter flow. The initial demonstrations of dark matter manipulation would likely involve modest achievements, the creation of local density variations measurable through gravitational effects on precision, inertial sensors, or the deflection of dark matter streams by infinitesimal angles, detectable only through statistical analysis of collision rates in detector arrays positioned upstream and downstream of the manipulation apparatus, building gradually toward more substantial control as theoretical understanding deepened and engineering capabilities advanced through iterative refinement of technologies initially developed for other purposes, adapted and repurposed to engage with this invisible substrate that pervades all of space, yet remains tantalizingly beyond the reach of conventional manipulation techniques. Within a dark matter manipulation facility, a research installation perhaps constructed in deep space beyond the gravitational influence and electromagnetic noise of planetary environments, or buried beneath kilometers of rock on the far side of the Moon, where cosmic ray backgrounds diminish and isolation from human activity reaches levels unattainable on Earth's surface. Specialized apparatus would generate controlled field configurations designed to create regions of enhanced or depleted dark matter density, establishing gradients in the invisible matter distribution that could be measured through their gravitational effects on test masses suspended in ultra-high vacuum chambers and monitored with laser interferometry capable of detecting displacements smaller than the radius of an atomic nucleus. The fundamental mechanisms enabling this control would operate through whatever interaction channels connect dark matter to the controllable parameters of our technological systems, whether through the generation of massive gauge bosons that couple to both ordinary and dark sectors, or through the modulation of scalar fields that permeate space and mediate between visible and invisible matter, or through the careful orchestration of quantum entanglement between ordinary matter systems and dark matter degrees of freedom, exploiting correlations that persist even across the divide between electromagnetic visibility and gravitational-only interaction. The initial applications of rudimentary dark matter control would likely focus on precision measurements and fundamental physics research, using the ability to manipulate dark matter distributions to test competing theories of particle physics beyond the standard model, to measure dark matter particle properties with unprecedented precision by observing how confined populations respond to applied fields, and to explore the phase space of possible dark matter candidates by determining which theoretical models remain consistent with observed manipulation behaviors and which can be definitively excluded based on their failure to produce predicted responses to control field configurations. The progression from laboratory-scale manipulation to engineering applications capable of affecting macroscopic systems would require extraordinary amplification of control field strengths and volumes, scaling from apparatus that influences dark matter within cubic meters of space to systems operating across cubic kilometers, then cubic astronomical units, each escalation in scale demanding advances in power generation, field coherence, and theoretical understanding that compound multiplicatively rather than adding linearly. The first practical applications of dark matter control at engineering scales would likely involve gravitational manipulation, using the ability to concentrate or disperse dark matter to create controlled variations in space-time curvature without the enormous mass concentrations that conventional approaches would require, potentially enabling propulsion systems that move spacecraft by generating asymmetric dark matter distributions that produce net gravitational forces, or defensive systems that create gravitational lenses to deflect incoming projectiles or radiation, or communication networks that transmit information through modulated dark matter density waves, propagating at speeds determined by the equation of state of the dark matter medium and the strength of whatever self-interactions these particles possess. The energy requirements for manipulating dark matter at scales sufficient to produce measurable gravitational effects on macroscopic objects would likely remain prohibitive for centuries after initial control mechanisms are demonstrated, as the total mass of dark matter that must be displaced or concentrated to generate forces comparable to chemical rockets or nuclear propulsion systems would measure in tons or megatons, each particle requiring individual interaction with control fields, the cumulative energy cost potentially exceeding the rest mass energy of the matter being manipulated unless the coupling between control fields and dark matter proves remarkably efficient, or unless natural dark matter flows can be redirected rather than created from ambient densities. Surrounding the technical challenges of dark matter manipulation would exist profound questions about the stability of existing cosmic structures under regimes where dark matter no longer remains a passive gravitational component but becomes subject to deliberate rearrangement by technological civilizations, as the gravitational binding of galaxies, the orbital dynamics of solar systems, and the large-scale structure of the cosmic web all depend critically on dark matter distributions that have evolved over billions of years through purely gravitational processes, establishing quasi-equilibrium configurations that might prove vulnerable to disruption if significant fractions of the dark matter components suddenly respond to forces beyond gravity. The galaxies themselves exist as stable rotating structures because their dark matter halos extend far beyond the visible stellar disks, providing the gravitational potential wells within which stars orbit in rough circular motion rather than following the Keplerian trajectories that visible matter alone would dictate, with rotation curves remaining flat at large radii specifically because dark matter density profiles decline slowly with distance from galactic centers, maintaining approximately constant circular velocities even in the outermost regions, where starlight fades to insignificance, and only the gravitational influence of the invisible halo keeps sparse populations of stars and gas clouds bound to the system. Any technology capable of redistributing dark matter on galactic scales would possess the capacity to fundamentally alter galactic structure, potentially causing spiral arms to wind up or dissipate, bars to strengthen or weaken, or entire stellar populations to be ejected from their parent galaxies as the gravitational potential wells they inhabit undergo restructuring, though the energy requirements for manipulating dark matter distributions across volumes measured in cubic kiloparsecs, each containing billions of solar masses of invisible matter, would likely exceed the total energy output of entire civilizations, unless the manipulation mechanisms prove capable of triggering cascading effects or exploiting instabilities in the existing dark matter distribution. Beyond the scales of individual galaxies, the cosmic web itself represents a structure defined by dark matter distributions, with galaxies embedded in filaments of enhanced dark matter density that connect massive clusters at the nodes where multiple filaments intersect. The entire network spanning billions of light-years and containing the accumulated gravitational influence of structure formation processes operating across cosmic history as initially smooth dark matter distributions developing from quantum fluctuations in the inflationary epoch gradually condensed under their own gravity, drawing ordinary matter into the emerging potential wells and enabling the formation of the first stars and galaxies when the universe cooled sufficiently for hydrogen atoms to form and gravitational instabilities to amplify density contrast to the threshold where gas collapse and star formation became possible. The ability to manipulate dark matter at these cosmological scales would represent a capability approaching what earlier eras might have attributed to cosmic architecture itself, the power to reshape the large-scale structure of the universe, to redirect the flows of dark matter along cosmic filaments, to enhance or diminish the growth of galaxy clusters, potentially even to influence the rate of cosmic expansion by manipulating the distribution of matter and energy density across volumes comparable to the observable universe, though such ambitions would remain purely theoretical for any civilization confined to even galactic scales of activity, as the light travel time across cosmic web structures exceeds the ages of typical stellar populations, and the coordination of manipulation efforts across such distances would require communication and control systems whose design challenges dwarf those of the manipulation technology itself. The philosophical implications of dark matter control would extend beyond questions of technological capability to encompass fundamental issues about the nature of reality and humanity's relationship to the cosmos, as dark matter represents not merely an engineering challenge, but rather a domain of physical existence that has remained completely separate from human sensory experience and direct manipulation throughout the entire history of our species, our civilization developing within the approximately 15% of cosmic matter that interacts electromagnetically, while remaining entirely oblivious to the gravitational influence of the dominant component until sophisticated astronomical observations and theoretical physics revealed its necessity in the mid-20th century. The transition from a species that exists solely within the electromagnetic sector to one capable of manipulating the gravitationally dominant dark component would represent an expansion of human agency into realms previously accessible only through theoretical inference and statistical measurement, potentially revealing entirely new categories of phenomena, structures, and interactions that remain invisible when dark matter can only be detected indirectly through its gravitational effects, but become apparent when direct manipulation enables detailed probing of dark sector physics. The possibility that dark matter particles might themselves organize into complex structures held together by dark sector forces analogous to electromagnetism, but operating only within the dark component would remain entirely invisible until manipulation technologies enable detailed mapping of dark matter distributions at scales fine enough to resolve such structures, potentially revealing an entire shadow biosphere or even shadow civilizations existing in parallel with ordinary matter but remaining undetectable through electromagnetic observations and gravitationally invisible, unless they achieved concentrations far exceeding ambient dark matter densities. The development of dark matter control technology would necessarily proceed through stages of increasing capability and confidence, beginning with fundamental research that identifies the particle nature of dark matter and establishes the basic theoretical framework relating dark sector physics to the standard model of particle physics, progressing through proof-of-concept demonstrations that achieve measurable manipulation of dark matter distributions in controlled laboratory settings, advancing to engineering applications that exploit dark matter control for practical purposes such as propulsion or gravitational engineering, and ultimately perhaps reaching civilization-scale capabilities that reshape galactic structure or redirect cosmic evolution, each stage requiring not only technical advances but also the development of new scientific disciplines, new mathematical frameworks, and new philosophical perspectives adequate to comprehend humanity's changing relationship to the cosmos as we progress from observers of natural processes to potential participants in cosmic architecture. The timeline for such development would likely span centuries or millennia rather than decades, as the fundamental physics required to understand dark matter interaction mechanisms remains unknown despite decades of intensive experimental searches, and the engineering challenges of scaling from particle physics experiments to macroscopic manipulation would require sustained effort across multiple generations of technological development, with each advance opening new research directions and revealing previously unsuspected complexities in dark sector physics. The social and political implications of dark matter control would grow increasingly profound as capabilities advanced, beginning with relatively modest impacts when manipulation remained confined to research laboratories and specialized facilities, but expanding to encompass questions of cosmic governance, environmental protection at galactic scales, and the responsible stewardship of technologies capable of disrupting the gravitational equilibrium that enables stable stellar systems and the persistence of habitable planetary environments. The ultimate consequences of developing dark matter control would depend critically on the specific properties of dark matter particles and the nature of their interactions with ordinary matter and with each other, parameters that remain uncertain despite extensive experimental constraints and theoretical speculation, as observations establish only that dark matter must be stable on cosmological timescales, that it must interact very weakly with ordinary matter through non-gravitational forces, and that it must have been present in appropriate abundances during the early universe to seed the formation of the large-scale structure observed today. If dark matter consists of particles with no interactions beyond gravity, then control mechanisms would necessarily operate through gravitational means alone, requiring the generation of precisely shaped gravitational fields or the manipulation of space-time geometry at levels demanding technologies that approach or exceed those required for general relativistic effects such as significant time dilation or gravitational wave generation, rendering practical applications extraordinarily challenging and perhaps permanently beyond reach for civilizations constrained by thermodynamic and relativistic limitations. Alternatively, if dark matter particles possess weak interactions with ordinary matter through portal interactions mediated by massive force carriers, or through mixing with standard model particles via higher dimensional operators, then manipulation technologies might prove more accessible, exploiting these coupling channels to generate control fields using extensions of familiar electromagnetic or nuclear technologies, adapted to resonate with the specific interaction, frequencies and field configurations that couple to dark matter's quantum numbers. The discovery of dark matter self-interactions, forces operating within the dark sector itself that allow dark matter particles to scatter off each other or bind into composite structures, would dramatically expand the possibilities for manipulation and control, potentially enabling dark matter chemistry, dark matter engineering, and the construction of purely dark matter structures that interact with ordinary matter only gravitationally, but possess internal complexity comparable to or exceeding that of electromagnetic matter, opening speculative possibilities ranging from dark matter computers to dark matter organisms, entire categories of complexity existing in parallel with the familiar electromagnetic world, but remaining invisible until manipulation technologies provide the means to probe and interact with dark sector structure at fine scales. Across all possible scenarios for dark matter control, from modest laboratory demonstrations to civilization-scale cosmic engineering, the fundamental transformation would involve humanity's expansion beyond the electromagnetic domain that has bounded all of our sensory experience, all of our technology, and all of our direct interaction with matter throughout our evolutionary history and the entirety of recorded civilization, reaching into the gravitationally dominant component of cosmic matter and establishing the theoretical understanding and technological capability necessary to sense, manipulate, and ultimately incorporate dark matter into our expanding sphere of agency and comprehension. The journey towards such capability would necessarily proceed through patient accumulation of knowledge, careful experimental verification of theoretical predictions, and gradual development of manipulation technologies starting from the most fundamental scales and advancing only as understanding and capability permit, each stage building upon previous achievements and opening new questions even as it resolves old uncertainties. The process itself exemplifying the character of scientific progress as an endless frontier, where each answer generates new questions and each achievement reveals previously unsuspected depths of complexity. The cosmological context within which this development would occur, the fact that dark matter represents approximately 85% of all matter in a universe that extends across billions of light years and contains hundreds of billions of galaxies, each embedded in its own dark matter halo and connected through the vast filamentary structures of the cosmic web, suggests that any civilization achieving dark matter control would confront not merely a new technological capability, but rather an expansion of perspective that repositions intelligent life from occupying a small corner of the visible universe to potentially engaging with the dominant component of cosmic matter, a transition whose full implications would unfold across timeframes measured in cosmic evolution timescales rather than human historical periods, as the slow processes of galactic dynamics, large-scale structure evolution, and cosmic expansion provide the context within which any dark matter manipulation would ultimately operate and within which its consequences would propagate across the vast scales of space and deep time that characterize the universe's ongoing evolution.